This video we're going to cover section 6.4, which is the first of two sections on logarithmic functions. Alright, so again, classic thing for us to first do in an algebra textbook here is define the logarithm. So the logarithm has a base of a, and we're going to, again, just like exponentials, only consider bases that are positive and not equal to 1. And it's denoted as y equals log base a of x. And it is defined really as the inverse of the exponential. So notice here that for this logarithmic function, x is the input and y is the output. And then in this exponential, the y is now the input of the exponent and the x is the output. So we're literally defining the logarithm to be the inverse of the exponential here. All right. All right, now before we get too deep into that conversation of the inverses, let's first just do a little bit of skill building. All right, so some of the homework problems that you're going to have are going to ask you to convert, if you will. So you're going to convert between an exponential form to a logarithmic form or vice versa. You'll be given a logarithmic form and asked to convert to an exponential form. So let's practice a couple of those problems here together for some examples, right? So again, just reminding myself of this definition, right? I want to point out to you here again, right? The base of the logarithm is the base of the exponential, right? The input to the log is now the output to the exponential, right? And the output of the log is now the input to the exponential, right? Now the exponent. So log base 3 of x equals y is the same thing as saying x equals 3 to the y. So again, base of the log, base of the exponential. Input to the log, output to the exponential, right? And output of the log is now the exponent. Another example here, right? If 4 equals log base 3 of 81, that is equivalent to 3 to the power of 4 equals 81. And we know that that's true, right? We take our calculator and compute that value. Right? If we have y equals log base 5 of x, then that's equivalent to 5 to the power of y equals x. So 5 to the power of y equals x. Let's plug a number in for x and y here, make sense of this, right? So if I have negative 1 equals log base 5 of 1/5, that's the same thing as 5 to the negative 1 power equaling 1/5. And again, we know that that is a true equation. All right, let's do some more skill building here. So let's suppose on this example, we're going to be given a logarithmic equation and we're being asked to convert to an exponential equation. Right? So let's take letter A, right? So we're going to convert log base A of 4 equals 5 into an exponential form. So again, the base of the log is the base of the exponential. Right, and the way that I like to see this, I'm a visual learner, so this is base of A raised to the power of 5, and that will equal 4. Okay? So remember, the output becomes the input on the exponential, right? And the input becomes the output. So there's the A to the 5 equals 4. And then ditto for this guy, right? So this is going to become base E raised to the power of negative 3 equals B. And then you try letter C for me for a second. So pause the video, you try letter C, and then unpause and see if you get the same answer that we get. All right, so now that you've unpaused your video, hopefully what you did was following this definition, right? We said 3 to the power of c equals 5, and there's your exponential form. All right, now what if we go the other direction? So what if we're given an exponential equation and we're being asked to put into a logarithmic form? Right? So again, the base of the exponential will become the base of the logarithm. This is the input of the exponential. That's going to become the output of the logarithm. And then this is the output of the exponential. That's what will be inside the logarithm. So I'm going to have log base 1.2 of the number m equals the exponent of 3. Okay? And then ditto for here, right? So the base of the exponential becomes the base of the log. So I'm going to have log base e of 9 equals b. All right, so again, pause the video and you try letter C for me. All right, you've unpaused the video. So you should have log base A of 24 equals 4. All right? So the reason that we're spending a little bit of time on the skill here is when we solve equations that are logarithmic or exponential in form, this is actually the technique that we're going to use. We're going to rewrite the exponential as a log, or vice versa, rewrite the logarithm as an exponential. All right, now a second objective in this section is for you to evaluate a logarithmic expression. So for example, let's suppose we want to find the value of log base 3 of 81. Now notice there's no equation here, right? If I go back to that prior slide, I was given a logarithmic equation. There was already an equal sign in there, and I rewrote it in an exponential form. And that's really what I'm going to do here. So even though this isn't an equation, I'm going to make it an equation. I'm going to basically say, what does this number equal? So I'm going to say log base 3 of 81 equals what value? So now that I'm thinking of this as an equation, then I'm going to rewrite it. I'm going to say 3 to the power of question mark equals 81. And what we'll do is we'll use that knowledge that we had right at the end of the exponential section. I'm going to match the bases here. So 3 to what power equals, and I'm going to write 81 as a base of 3. So we know that 3 to the 4th power would have to equal 81. So we know we'd have to have 4 here, right? So log base 3 of 81 equals 4, because 3 to the power of 4 equals 81, okay? So I'm going to do the same thing with letter B here. I'm going to say log base 2 of 1/8 equals what value? I'm going to rewrite. I'm going to say 2 to what power equals 1/8. Now look, right here, if you can recognize the answer, awesome. Write the answer, right? Just like on this side. If you could have recognized 3 to the power of 4 equals 81, you saw that, write it. Write the answer, all right? But if you don't see that that's the answer, you don't see what the value is, then take it forward. So let's say 2 to what power equals 81? Excuse me, 1/8, right? And then match the bases. So on this side, I really have 1 over 2 cubed, which this is really 2 to the negative 3 power. So really, 2 to the negative 3 will equal 1/8. And there's the value of my logarithm, the negative 3. All right? All right, so the next objective here is for us to talk about the domain of the logarithmic function. Okay. Before we do that, what I want to do is make a connection to the fact that we have defined the inverse function. Right? So remember that first definition, what I pointed out to you was that we were defining the logarithm as the inverse of the exponential. So let's go through finding the inverse of the logarithm for the moment, right? So suppose I want to find the inverse of the logarithm. Remember we did this back in, 6.2, right? How did we find the inverse of a function? Well, the first thing we did was we got rid of the f of x symbol and we wrote it as a y. And then we interchanged the domain and range. So I'm going to interchange the x and the y in my equation. Now, when we did this in 6.2, we said technically we were done. At that step, this is the inverse. However, we want to solve for y. So to solve for y here, what I'm going to do is I'm going to rewrite into an exponential form. So I have this log equation I'm going to rewrite into an exponential form. Okay? And then that is the equation of my inverse. Right? I'm just going to, instead of having y equals a to the x, I'm going to call it f inverse is a to the x. Now, again, here's the reason that I did this, right? We know that the domain of a function is the range of its inverse, right? And we know that the range of a function is the domain of its inverse. We talked about that before, right? So, for example, right, we have 2 to the x and a log base 2 of x are inverses. And we know domain and range of each of those have to switch roles, right? E to the x and log base e to the x are inverses, right? So remember, for these exponential functions, the domain is all reals. So the domain of this exponential function will become the range of the logarithm. Right? So I have it, I'm saying it backwards than what I have down here, right? The domain of the exponential functions are reals, so that's the range of the logarithm. Right? And then ditto, we said that the range of the exponential function was strictly positive values. So that's the domain of the logarithm, right? So the range of the exponential function is strictly positive. That's the domain of the logarithm, all right? So I like to make the connection that they're inverses of each other. And that shows me what domain and range are for my new function in this section, the logarithm. Okay, so again, let me just point this out to you. So we're talking about domain. So if I look at this original equation, the log base a function, the domain is strictly positive values, right? So I can't plug negatives inside of a logarithm, and I can't even plug 0 inside of a logarithm, right? Here's the domain of my logarithm. So I can only take the log of a positive number, right? So when we go to this next slide, we're at finding domain, right? That's that concept that I'm going to use. So when I look at letter A and I say, you know, what's the domain of this function? I know the number that it is inside, right? The expression that's inside, x minus 2, has to be greater than 0. So that whatever x has solved that inequality, that is my domain. Right? And I'll just simply add 2 to both sides there and get x is greater than 2. That's the domain of letter A. I'm going to look at letter B. Letter B is a little bit more difficult. Right? But let's work through this, right? So I know that this thing inside the logarithm, x squared minus 9, must be positive. Now remember, when we did the quadratic function section, which was 4.3, we talked about solving quadratic inequalities. Now, when we solve this quadratic inequality, remember our approach was to graph the parabola. So I'm going to graph this parabola right here, and I'm going to ask, where is this greater than 0? So here's where the parabola has positive y values, is above the axis, right, greater than 0. And here's where the graph has positive y values, right, above the x-axis and greater than 0. So we want these x's out here. So any x less than negative 3 will make this positive and therefore be in the domain of the log, right? And any x greater than 3 will make x squared minus 9 positive, and then the log is okay. I'm logging a positive number. So there's the domain of my logarithm based on kind of a graphical analysis of x squared minus 9 being greater than 0. All right, now for letter C, I want to point out to you here, it doesn't matter if the base is fractional, right? We're still looking at the inside of the log having to be positive. So what I'm going to do for letter C, I'm going to take the same exact approach we did for letter B. Now I'm going to say where is x squared greater than 0? I'm going to graph the parabola x squared. I'm going to point out to myself that it's greater than 0 everywhere except right at the vertex. Right, so it's positive when x is greater than 0. It's positive when x is less than 0. So I just aren't allowed to have x equals 0 in this particular example. All right, so look, in my math lab, there's going to be a couple of questions where they say, you know, what's the domain of the logarithm? And all we'd have to remember is that the inside of the logarithm must be positive. It can't even be 0. Right? So I can't have negatives in a log, can't have 0 inside a log, has to be positive. Now this will come in handy when we start solving equations. So when we solve a log equation or an exponential equation, this will be a good way for us to check our work. We'll come back to this idea. All right, so the fourth objective here is for us to graph logarithmic functions. So think about the last section in 6.3, we had those two basic shapes of exponentials. And we could shift those right or left, shift them up and down. But we have those two basic shapes of exponentials. We're going to literally build the graphs of logarithms using those shapes. So again, remember the logarithm is the inverse of the exponential. Right? That was how we defined it at the beginning of this video. Also remember when we discussed inverses in 6.2 that the graph of an inverse and its original function, right, they're symmetric to each other about the line y equals x. So for example, if I were to graph the 2 to the x function that we did in the last section, right, this is the exponential, base is bigger than 1. And so it's increasing. So here's my increasing exponential. So we know the inverse of this function is log base 2 of x. And we know that the inverse has to be a mirror image about the line y equals x. So we know that the log base 2 graph must look like this, right? So I interchange domain and range. If x is 0, y is 1, then x is 1, y is 0. There's that mirror image over the line y equals x, right? On the exponential function, if x is 1, y is 2, then the point x is 2, y is 1 is on the graph of the logarithm. It's inverse, right? And ditto for this point as well, right? And all points in general. So here's the graph of the exponential, which we learned about in the last section. Here's the graph of the log base 2 function. And again, the concept here for this slide in particular is that we're constructing the graph of the logarithm based on knowing that the base 2 exponential and the base 2 log are inverses. Okay? Then let's make a base that's fractional. So let's suppose we have y equals 1/3 of x, and we know its inverse is log base 1/3. Okay? So again, if I played that same kind of construction game, here's my exponential in blue, right? 1/3 raised to the power of x. If I reflect it about the line y equals x, I get the red graph, log base 1/3. So in the end, we basically are going to have two basic shapes of exponentials. And here's, the kind of generic idea that we just talked about on the prior slide, right? Excuse me. If the base is fractional, we're going to get this red graph, this decreasing logarithm. If the base is greater than 1, we're going to get this increasing logarithm. And let me just point a couple things out to you specifically, and then there's a summary on the next slide. So remember that the exponential function on both of these graphs, so the blue exponential graph that decreases on the left and the blue exponential graph that increases on the right, those both have a horizontal asymptote. Right? Again, y cannot equal 0 here is a horizontal asymptote. Notice for the logarithm, x cannot equal 0 is a vertical asymptote. Again, on the graph on the left, y equals 0 is a horizontal asymptote, x equals 0 is a vertical asymptote. Right? Again, there's that relationship between a function and its inverse. Okay? And again, here's the domain visually, right? Remember, the exponential has a range of strictly positives, so the logarithm has a domain of strictly positives, right? We can see the vertical asymptote, horizontal asymptote connection there. We can see the domain and range connection. So here's a little summary of those two, right? So two basic shapes that we're going to learn about for logarithms. If the base is bigger than 1, it's an increasing logarithm, has a vertical asymptote at x equals 0. If the base is fractional, right, but positive, it's going to be a decreasing logarithm, and again, vertical asymptote at x equals 0. So one of the things you're going to do in this section is you're going to use those two basic shapes, and you're going to shift them and use transformations to graph them. Now, in particular, remember on the last section we talked about the base e exponential function, that in the real world, right, our applications are going to involve base e exponentials. So same thing's going to happen in this section. We're going to talk about the base e logarithm. Right? So what we typically do is we call the base e logarithm the ln function. Right? So I want you to notice that they use lowercase ln, and every math book is going to use lowercase ln. And I want to point out to you that on your calculator, the L and N are capitalized. Right? So on your calculator, this is the natural log, and notice the Texas Instrument producers of your calculator made it and the base e exponential the same button, right? So they're trying to remind you that these are inverses of each other, right? So ln is log base e, and then if I do second ln, that's the base e exponential. So again, we kind of have some laziness going on here where ln is our shorthand notation for log base e. So just wanted to remind you of that, right? It would not be wrong to write log base e, right? But you don't see that in the textbook. You won't see that in my math lab. So if you're graphing equations or you're typing things into my math lab, it's always going to be ln, and it's always lowercase l and lowercase n. Now remember that this is a, here's my increasing exponential. So here's my increasing logarithm graph. right? So bringing up my calculator, I hit the y equals button, and if I just come down here and punch the ln key, notice how it makes it lowercase there, and then I hit X, and I'll close my logarithm, and if I graph, there's my log base e function. Right? And if I bring up Desmos, on my keyboard, I could just type ln, or I could punch the little ABC button here, and I could just do ln. And if I do ln, it now knows I'm talking about log base e, and then I'm going to do ln of x, and it's going to graph the log base e function for me. All right, now let's kind of tie all of this together here. So in this example, we're being given the function negative ln of x minus 2. All right, so we're being asked to do 6 things. Right, let's work on this together. So part A says find the domain of the logarithm. Now remember, to find the domain of any logarithm, I have to have what's inside the logarithm be strictly positive. So if I take what's inside the logarithm, set it to be greater than 0, that gives me a domain of 2 to infinity. Now, letter B says to graph the logarithm. So if I use transformations, right, I'm going to start with the basic log function. Here's basic ln, right, my log base e, my increasing function. Right? And then I'm going to go ahead and reflect the graph. So I'm going to graph the negative ln of x. I'm going to flip the graph upside down. And the last thing I'll do is I'll shift the graph 2 units to the right. And there's my final graph. So again, just want to remind you, here's a vertical asymptote at x equals 0. That's going to get moved 2 units to the right. And there's my rough sketch of my logarithm. And letter C says, from that graph, determine the range in the vertical asymptote. Right? Now, obviously, the range I can see is going to go all the way to positive infinity on my y-axis. And as it comes down, it will cover all the way down to negative infinity on my y-axis as well. So my ranges are reals, and I can see my vertical asymptote is x equals 2. Now there are 3 other parts to this question, so let's answer those. It says find f inverse of my original equation. So my original equation was y equals the opposite of ln of x minus 2. So I'm going to interchange the x and y variables. So I swap domain and range. And again, this is my inverse equation, but we always solve for y. So first thing I'm going to do to solve for y is I'm going to divide this -1 coefficient to the other side. And now that I've got the ln all by itself, I'm going to rewrite it in exponential form. So remember, this is log base e. So that's going to become e to the power of -x, and that's going to equal what's inside the logarithm. So I'm rewriting this just like we did at the beginning of this video. And then now I'm just going to add the 2 to the other side, and there's my inverse function. I have solved for y. All right, now letter E says use f to find the range of f inverse, right? So check this out. The range of my inverse would be the domain of my original function. So let me go back to that prior slide. And let's point out to ourselves the domain of this function would be the range of the inverse, right? So what's the domain of this function? Well, we said the domain was x greater than 2, right? Here was the domain, and we can see it on the graph, anything greater than 2. So that's going to be the range of my inverse. Right? So the range of the inverse is the domain of the function. That was greater than 2, so this is greater than 2 for my range. Right, and then the last part is to graph f inverse. So what I did was I graphed the original function. Here's my blue function from the prior slide, and then I just do the mirror image of that over the line y equals x, and there's the graph of my inverse function. Now I want you to keep in mind here, we graphed exponentials in the last section, so I should be able to graph this exponential without ever knowing the original logarithmic graph. Right? I know how to graph an exponential. However, the point of this section was for us to connect to that idea of those being inverses. All right, now look, let's suppose I wanted to check this. So let me bring up Desmos real quick. And let's suppose I wanted to graph my log function. All right, so I had negative ln of x minus 2. So I'm going to punch the negative sign, and then I'm going to do ln of, and then I'm going to use a paren. So I'm going to hit the parenthesis here, and I'm going to type x minus 2, x minus 2. So that's my original graph that we had sketched, right? And then I have my other function, my other inverse, and that was e to the negative x plus 2. So again, I'm going to type e, and then I'm going to go back to the exponential function. I'm going to type negative x, and then I'm going to hit my little right arrow button over here to get off the exponent, and then type plus 2. Right, and so I can see there's my original and there's my inverse. And then, maybe just for visualization purposes, I can graph y equals x, and I can see the mirror image of those two graphs, and that's a nice way to check my work of finding my inverse function. All right, now there's one other equation that we're going to see occasionally, and that's the base 10 logarithm. All right, so what we typically do is we write log of x, and we don't write the base. All right, so if you see a log where the base is missing, right, normally we write the base down here as a subscript. So if the base is missing, then that's understood to be base 10. Right, so x equals 10 to the y is the inverse of log base 10 of x. Now again, we're being lazy. We're leaving the base 10 off. We're writing it as log of x. And just to point out to you again on your calculator, here's the log key on your calculator. And above it is the 10 to the x key. So again, it's like the people at Texas Instruments. We're trying to do you a favor and remind you that those are inverses of each other. Right? And then again, here's the 10 to the x function in blue. Here's the log base 10 function on your calculator. All right, now real quick, one thing I want to point out to you here, right? So remember when we were graphing exponentials earlier, like we might have graphed y equals 2 raised to the power of x. We might have graphed y equals, 5 raised to the power of x. We might have graphed y equals 10 raised to the power of x, right? Oops. I just freaked Desmos out here, right? See if that will work. Nope, that won't work. Let me see if I can cut and paste. Hey, that worked. All right. So again, just as a reminder, right, the bigger the base, the quicker the exponential grows. So here's my 2 to the x, here's my 5 to the x, here's my 10 to the x. Now, when I reflect those and create their inverses, right, the graph that grows faster as an exponential is going to grow slower as a logarithm, right? So let me just point out to you, log base 10 of x, that's going to be the slowest growing logarithm. If I graph log base 5 of x, let me see if I can do this here. So I would have log base 5. All right, so the easiest way to do this is to hit the functions button, tap on miscellaneous, and you can see the log key. So notice that when I type that, it puts the cursor in the base. So I'm going to type 5, and then I'm going to go ahead and hit my right arrow and jump to the inside and type x. All right. So there's log base 5. So again, notice log base 5 right here is growing faster than log base 10, right? So anyway, so the base 10 exponential grows the fastest, the base 10 logarithm grows the slowest. All right, so let's take a look at one more example here where we're going to solve a logarithmic equation. So we got two examples here, right? So this first example says solve the equation log base 2 of 2x plus 1 equals 3. So honestly, the only thing we're going to do here is we'll rewrite this logarithm in an exponential form. So I'm going to write this as 2 to the power of 3 equals 2x plus 1. I'm going to use that definition that we used back at the beginning. I'm going to say 2 to the power of 3 equals 2x plus 1, and then I'm going to isolate the x. So I'll subtract the 1 to the other side. 2 cubed is 8. I subtract the 1 to the other side, and then I'm divide both sides by 2, and I get the solution of x equals 7/2. All right, and then the second example, we have log base x of 343 equals 3. Right, and so if I rewrite this logarithm, I'm going to have x raised to the power of 3 equals 343. And now solving this equation, I'm going to have to cube root the left-hand side and cube root the right-hand side. So I find out that that would be x equals 7. All right, so if we do one more example here where we have a base e exponential, right? So in order to solve this exponential equation, the first thing I'm going to do is isolate the exponential term. right? So I'm going to take this 2 and divide it to the other side, and it gives me e to the 3x equals 3. Now that I've isolated the exponential, I can rewrite it as a logarithm. So I'm going to rewrite this as log base e of 3 equals 3x, right? So this is the base of the logarithm. This is the inside of the logarithm. This is the output to the logarithm. So I'm almost done solving for x, so I'm going to divide both sides by 3 over here, and I'm going to get 3x equals 1/3 ln of 3. Right, and then, feel free on all 3 of these equations to check your work. I mean, I definitely would check my work here, right? So I'd take out a calculator and I'd find out what 1/3 ln 3 is, and I'd plug that number back into my original equation and check the work there. All right, so quick summary here of what we talked about in this section. We talked about logarithms. We technically defined the logarithm to be the inverse of the exponential. We talked about if the base was bigger than 1, I had the increasing logarithmic graph. Right? We had a vertical asymptote of x equals 0. Right? This was increasing. And then if we had the base less than 1, right here, right? This was the decreasing exponential function. All right, as always, if you guys have questions, please post on the discussion board in black.